All right, so continuing with our introduction to differentiation, just first recall that there's a number of different styles of notation you can use to show a derivative, and we've seen this before. For example, if we're looking at a function f, then we could say f prime of x to denote the derivative, or df dx, or d dx of f. These are all equivalent. If our function is representing the position of an object, well, then its change, its derivative, is the same as its velocity. And that idea will work, as a fairly common idea. If you've taken some physics, the change in the position relating to velocity is a old idea. But let's look at this. I have a function, and you can see it's been graphed here, this cubic function that only exists between 0 and 15, and it represents the position of an object after x minutes. All right, so first, if I want to find the average rate of change, the average velocity of this object over this period, well, that means I don't need any calculus. I just need some simple linear, our knowledge of linear functions, which is the average rate of change, the average velocity is just the slope from the beginning to the end. And so I can imagine just what's the slope of this secant line here. And that will be the average rate of change. And so if I look at this line to find the slope of that, I can just see that my y2 minus y1, my change in height is 1,000. My change, I shouldn't say change in height, I guess I should say change in position. My change in x, which in this case is time, is from 15 take away 0, so just 15. And we get exactly 66.6 repeating. And the units of that, which are always going to be important for this, are meters per minute. Because again, x-axis is in minutes, y-axis is in meters. Keep in mind on most IB questions on an assessment, if you don't put the units down or the correct units, you'll rarely get the full marks. Most of the time, part of the mark is, or the mark is dependent on having the correct units. So always think about units for these. All right, so that's the average rate of change. And if I want to find the average rate of change from 0 to 10 minutes, then it would be the same idea. I would look at this sort of secant line right there. So while it's important, we don't need to linger on that anymore. We want to now more focus on the instantaneous rate of change, the velocity at different times. In this case, when x is 15 and when x is 5. Well, when x is 15, I can just see right there, as we saw in previous lessons, my tangent line appears perfectly horizontal. So while I'll confirm in my GDC in a bit, I can be pretty certain that that has a derivative that equals 0. And that's an important idea, that when we have a horizontal tangent, the derivative, the instantaneous rate of change, in this case, the speed, is 0. So at that instant, this object has stopped moving. And we can confirm that in a bit. However, the other one here, when x is 5, we saw in previous lessons that we could estimate the rate of change at first. Come back here. And so I'll draw the tangent line, but I'm not going to estimate its slope. And ideally, from previous lessons, we are quite aware about how we can find that right there. And so I want to find the derivative for this one. I want to find f prime at 5, which on your GDC, you first want to graph the function. You want to make sure your window settings are appropriate for what we're looking at here. So it's pretty straightforward. Just make your x min 0 and your x max 15. And your y min 0, your y max around 1,000, maybe a bit more. And then, like we've seen before, select your value. So when x is 5, you should get a derivative of approximately 88.9. And again, the units are important, meters per minute. And just to confirm, if you do the same thing at 15, you'll see you get exactly 0 or incredibly close to 0. Remember, what your GDC gives you is an estimate, so I can see it is actually 0 meters per minute. It's not moving at that point. All right, so what's the maximum velocity of this object? So for this, the maximum velocity is when the slope of the tangent is the steepest. And I can estimate it, it's somewhere around here, but I don't know where. You may assume it has to be halfway. I wouldn't assume that. It looks like it might be. Halfway is right there. But please don't assume that's always going to be its maximum. In many circumstances it is, in many it's not. So it's definitely around there. But what is that, where is that point, and what is that slope as well? All right, so first, to do this, I really need to now focus on just the graph of the derivative. And we found using our GDC, we've seen how we can find the derivative at certain points really quickly. We can also use our GDC to actually graph the derivative. And this again depends on your GDC. So I'm just gonna go to Desmos here, but here is the same graph I was just working with. And in Desmos, once you type in a function, I've called it f of x. If I just type a new function where I put d dx beside it, or if I just put f with an apostrophe, it'll know it's the derivative. Now, clearly you can't use Desmos on a IB examination, but everything I'm doing here, your GDC can do. It's just maybe not as quick. And so if I graph the derivative in the same scale, especially on the x-min and x-max, I can see in green in this case, this is the graph of the velocity. I can see at the beginning the velocity, maybe I'll turn off this previous graph. I can see at the beginning the velocity was 0, it gets faster, and then it slows down and comes to a stop. And so right there is my maximum of my derivative function, which means that is the maximum velocity this object will ever reach, which I can see is indeed, I now know, at 7.5, so it really was halfway, and that maximum velocity was exactly 100. And so how to graph this derivative is dependent on your GDC. Just keep in mind, quite often you'll want to change the scales of your y-axis. In this case, if I look at my original function, my function goes from 0 to 1,000 on the y. If I look at my derivative, it only goes from 0 to 100. In this case, I could still see what I need, but quite often you want to change your y max so that you can actually see the function clearly. And so to just answer this now, the maximum velocity was 100 meters per minute when x equaled 7.5 minutes. So at this point, please, there's no point going on until you first learn how to use your GDC to graph a derivative. It's very, very easy to do in Desmos for the most part. It's not much more difficult on the GDCs I'm aware of. It's just, like I said, it's probably a bit slower, but it can be quite a powerful tool. So next, I have some data here on the population of the US over 3 different time periods, from 1800 to 1900. And so first, I want to find the average rate of growth. And again, as soon as you see that, the average rate of growth, then we know we're just finding the slope between 2 points. Should be quick, and we definitely don't want to forget how to do that. So the average rate of growth between 1800 and 1850, I just wanted to find the slope between those 2 points. And so from 1800 to 1850, it's going to be the rise is going to be 23.1 minus 5.3. Looks kind of like a big fraction there. Divided by 1850 minus 1800, so just 50 over 50 years. And for this, we should get approximately, or I think it's actually exact, 0.356. Remember the units in this case, it's millions of people per year. All right, and then same idea for 1900 to 1850, or 1850 to 1900. Not 1900 hours, 1900 years. There we go. And so if you do this, you should get, again, 76 minus 23.1, your numerator, divided by 50 years, and you should get approximately 1.06 million people per year. So clearly over this time period, the population of the United States the rate of growth is definitely increasing, at least between those periods of time. All right, with that said though, I want to now try to come up with something a bit more accurate, or not, essentially we're just looking at a simple linear function here. But what I have here, essentially, if we imagine this graph and we just connect the dots with line segments, which it's not terrible by any means, but chances are that's not how the population was changing. So we'll look at one of 2 different regression models. First being exponential regression model, which we've used a number of times earlier in the course. For this, when I put this into my GDC or Desmos, I'm going to use in a moment, the only thing I would do for my table is instead of putting 1800, I would just call that 0, I would call this 50 and call this 100, and just realize my x values represent years from 1800. It tends to give us easier values to work with our regression equation. And I'd rather, it's pretty nice just 0 being 1800. As long as we don't forget what that is, I would always generally recommend that, because it doesn't actually specify the sort of how we have to set this up. So when I do that, if I go back to Desmos here, Here's the table. Now again, I gotta adjust my window settings here. Here, I wanna see at least 100 years into the future from 1800, and I really wanna compress this. There we go, because remember my Y scale is in millions. So adjusting my window settings, this is the data points we've been given. If I come up with a regression equation that's exponential, you should get something like this. And it has a decent, correlation, looking at the points, although it is just 3 points. And keep in mind, if I zoom out, at some point, the population of the country won't keep growing like this. But looking at this time period, it seems like a decent model. And let me just write down that equation. Keep in mind, this equation here is not for x being 1800 when it's at the start, it's when x being 0 at 1800. If that makes any sense what I just said, but I'm going to go with it. And so for this, you should get approximately, I'll write these down to 3 significant figures, but I'll use the exact values, and you should always do the same thing. Use the exact values in your calculator. Right, so this is what I get from my regression equation. Again, this is if 1800 is x equals 0. If I left just the years in there instead of putting 0 for 1800, you get a similar equation, but your A value would be significantly messier in my opinion, but it's a matter of opinion. In this case though, I can now look at my derivative, and you can, once you have your equation in your GDC, if I just want to find the instantaneous rate of growth at 1850 I should say, at 1900, that should be very, very quick from previous lessons. So in 1850, when you find dy dx, you should get about 0.560, 3 significant figures, million people per year. And in 1900, you should get about 2.12 million people per year. All right, that's it. Exponential model is great. If I just look at this graph, though, again, like I've stated, it's, I think, a pretty good model for this time period. As we start going more and more into the future, I feel less and less confident that this is such an accurate or useful model. For example, right now, the population of the United States is, 330-ish million, if I'm correct. And, according to this, it's by the year 2000, it's at, over 1 billion. So clearly this model is not valid when we get too much past 1900. So another model we want to look at is a logistic model, which is what I have here, logistic models we saw earlier in the course, and they have this sort of shape, which for this data does seem to be a more appropriate model, especially if I want to extrapolate beyond. Although again, as soon as we're extrapolating, we got to realize we can't put always too much faith into that extrapolation, but this seems a bit better than before, especially when I compare the two together. They start to diverge a lot once we get into the 1900s. They diverge greatly. And if I had to pick one, I think the logistic model would be a better one to use. And again, what I'm going to write down for my logistic model, which your GDC can find quite quickly, is all based on 1800 being x equals 0, like I said before. And you should get in a logistic model approximately 189 divided by 1 plus 34.7 times e to the negative 0.0315x. So with that said, once you have your regression equation and your GDC, should be very, very quick to find the instantaneous, the rate of change, the derivative in any sort of time period. So in 1850, this time your derivative should be about 0.639 million per year. Notice just a little bit more than we had with our exponential model. Not a huge difference though. I'll get a bigger difference here. In 1900, my dy dx should be about 1.43. So now getting significantly less than our exponential model. Just from the data I have, I can't say for sure it's better, but it does, I think it's probably better just knowing what I know about what the population of the United States is now. But either way, just from the data we have, we can't actually say for sure the logistic one is better. However, that's what we want to use for the last question. So for the last question, use that logistic model to predict when was the maximum growth rate of the United States and the year with which this occurred. And keep in mind, the more we have to extrapolate, the more invalid a number may be, but we can still make a prediction. And so using our logistic model, so going back here, I can tell it's going to be somewhere in here. Now, if you remember a fair amount from logistic models earlier in the course, you may recall the maximum rate of change you can calculate by knowing some of the values here. However, I don't expect us to remember that off the top of our heads right now. And if we have access to a GDC and understand derivatives, we don't need that actually. So what I want to do, like we've done before, is I want to graph the derivative of this function, which again, there's different ways of doing it. And when I graph the derivative of this function, I get what you see in red. Now notice this time, it looks almost like a horizontal line. It's not, and that's because, again, the scale of my y is right now set up for the population of the country, which I want to think in its rate of change. And so I'm going to turn off my old one. I'm going to adjust my y scale. And this is a much more useful graph to look at. This is showing me the derivative of the population of the United States based on the logistic model. And so the maximum population change, the maximum derivative, appears to be right here at when x is 112.7, so I'll round it to 113 to 3 significant figures, which, keep in mind, is from the year 1800, so that's 1913. And the maximum population change seems to be about 1.49, roughly 1.5 million people per year. So according to our logistic model, maximum is when x is approximately 113, so more importantly to say in the year 1913, when the rate is approximately 1.49 million people per year. Keep in mind, we are extrapolating past our data, not a huge amount, but we always want to keep in mind the significance of or the validity of our number when we're extrapolating may not be as valid as we'd like it to be.